Hi, it's Allison Buttenheim back with Module 2 for our Experimental Study Designs Week. We're going to talk about power and sample size calculations in experimental studies. Lots of learning objectives here. This is pretty dense material. It's from the beginning of Chapter 8 in Gordis. And for the purposes of our course, I don't expect you to be able to calculate complex sample size calculations or understand clustering or anything like that, but you should really understand what a type 1 and type 2 error is, how to go about using a table for sample size calculations and rules of thumb, understand the basics of how sample size goes up or down depending on your study parameters, and some issues around underpowering and the ethics of experimental studies. Okay, so why do we do sample size calculations and power analyses? The key question we're trying to figure out is how large a sample do I need, because samples are expensive. So how big a sample do I need so that I can actually detect meaningful differences between the intervention and the control group? And the theoretical framework underlying it is, we're doing these studies on samples of populations. We've talked about this a lot. And we want to be able to draw correct inferences to that population from the study that we do. So we need a sample that's large enough so that we can say with confidence that the observed differences that we saw are real. They didn't happen by chance. We can say something about the underlying population from which we drew our sample from the study that we've done. So you might want to check out Gordis on page 148. There's a nice table that talks about type 1 and type 2 error. I will confess, as a practicing epidemiologist, that I always have to go back to the book and look and see which one is which. So it's nice to have a good table in Gordis that you can copy and staple to your forehead. So we think about conducting an experimental study and drawing some conclusions from the differences we see or the lack of differences we see. And when we do that, we can't observe reality, but we know there are basically 4 conditions that must apply, one of which must apply. So I can observe that the treatment and control groups are different when I run my study, and in reality there's no real difference. Or I can observe a difference, and it turns out that that's a real difference in the population. It may be that I detect no differences in the 2 groups in my study, and that's true in reality as well. Or I may not detect a difference, but in reality the treatment and control are different. And so we can see there is in 2 conditions I'm correct, and in 2 conditions I'm in error. And we can actually organize those scenarios into a good old 2x2 table, again mirroring the Gordis table, where I've got the decision that I'm making from my study here, and the reality that I can never really observe here. And here T is treatment, and C is control. So in the 2 diagonals, I'm correct. Treatments and controls are actually the same. Treatment and controls are actually different. In this cell, I've got what we call a type 1 error, and we label that probability alpha. And in this cell, I've got what we call a type 2 error, and we label that probability beta. While we talk about beta sometimes, we more often talk about the inverse, 1 minus beta, which is often referred to as the power. And that's basically the probability of actually detecting this difference that exists in my study. So when we talk about a study being appropriately powered or adequately powered, we mean, can it find a difference in the treatment and control, assuming there is one underneath? And alpha is just when we also know it as a p-value in our statistical significance tests, it's basically the chance of a false positive. How likely is it that I'm going to say, yes, there's a difference, when in reality the treatment and control are actually the same? So I want to minimize my type 1 error, and I want to maximize my power. So how do we use this concept of type 1 and type 2 error and alpha and power to actually calculate a sample size? Well, you need to round up some parameters. One thing you need to know is what difference you're looking for. So what difference do I expect, or do I want to be able to detect in my study between treatment and control? And we often call that the effect size. I need to know what the current event rate is, or treatment rate or success rate, in the control group or in a similar group. So I need to know, if I want to look at a new medication and I want it to work 80% of the time, I need to know what the current one does. Is it 20%? Is it 10%? I need to choose my level of alpha, and I need to choose my power. And once I have those 4, I can begin to figure out a sample size. So let's use an example. For this, we're actually going to use the sample size tables. They're provided in Gordis on page 151. And in this scenario, we're going to use our control group is going to be an existing drug, which has a cure rate of 40%. And we have a treatment. We have a new drug we want to try. And of course, we don't know the cure rate because we haven't tried it yet. But we're looking for an effect size of 20 percentage points. We want to be able to say, yes, this new drug is at least 20% more effective than our control. We're going to set alpha at 0.05, which is a pretty standard choice. You can always justify that in a power calculation. And similarly, a power of 80%, which is a very standard choice. We also need to say that we're going to do a two-sided test. And by two-sided, we mean we want to be able to detect a difference in either direction from our control group. So we assume our treatment's going to do better, but we want to power the test so that we would actually be able to detect it if it were 20% worse as well. So if you find the relevant figures in table 8.4 for a 40% underlying rate and a 20% expected change, the table's already set up for alpha 05 and power 80% and two-sided, you'll see, hopefully, you can find the cell that shows you that you need 97 people in each group or 194 total. So you can also use that table, though, to kind of look up and across and down and over and see how sensitive your sample size is to changing some of these parameters. So if you think for a moment, and then you can check in the table, what if the existing drug is 50% effective instead of 40%, but you still want to maintain that effect size of 20%? Think for a bit, theoretically, do you think the sample size will go up or down? And then you can check that in the table. And what if you're looking for a smaller effect size instead of a larger effect size? What if you only need to detect a 10% difference instead of a 20% difference? Think again, make a guess about whether the sample size is going to go up or down, check it in the table, and then think about whether that matched your expectations and why the sample size would move in that direction when effect size goes down. Finally, if you can justify having only needing a one-sided test, you can turn the page, and there's the same table for one-sided tests. And again, think about whether you're going to need more or less people, more or fewer people in your study if you're only doing a one-sided test. And see if that matches your expectations. Another way to do kind of quick and dirty sample size calculations, this is really back of the envelope because the formulae aren't that precise, but there are some basic rules of thumb that were developed before we all had ready access to online sample size calculators. It's basically a formula that uses P1 and P2, which are the event rates in your treatment group and the event rate in your control group, and a ratio of the two, R, which is P1 over P2, to calculate N, the sample size for each of the two groups. And it uses a constant here, in this case it's 7.85, and that 7.85 is determined by using alpha of 0.05 and power of 80%. If you want to change alpha or change your power, you're going to end up with a different constant right here. So let's try another example with these kind of rules of thumb here. Here we've got a new device, and we're comparing it to an existing device with a 40% failure rate. Of course, failure being a bad event. And we want to be able to detect whether our device can do any better. Can it get down to a 30% failure rate? Can we observe a 10% percentage point drop in the failure rate? So for alpha 0.05, power 80%, two-sided test, try using the formula here to calculate the group size required. And I would suggest stopping the video at this point and calculating this manually, see what you get. All right, so we've got P1, we had 30%, P2, 40%. The ratio is 0.75. We can plug those in here to the formula. And I got 353. Hopefully you've got something similar. Now, of course, you can also use these same parameters to go back and check in the Gordis table whether they come up with a similar answer. And I believe they get 360. So we're in the right ballpark. Some other options for calculating sample size. There are about 1.5 billion online sample size calculators. I've given you a link here to one, and you could definitely try rerunning this same example with this device on this calculator and see what you get. I'll give you a hint. The formula for the rule of thumb formula, they're framed as failure rates. You'll actually need to reframe that as success rates to use this particular online calculator. But once you do that, you should again get get right in the ballpark for sample size. Finally, probably my strongest piece of advice is to just get really friendly with your statistician. Statisticians are very important members of teams for experimental designs. Find one who is kind and patient, but also who can explain the choices that you're making together in ways that you understand, and especially what the trade-offs are with sample size. They are like gold, and treat them as such. There's a neat paper that maybe I'll give you the citation for by Schultz and Grimes, and it just goes through sample size calculations and theory in a very accessible way. And they talk about the sample size samba, which I think is a great expression. How investigators can and do tweak different parameters of their study to get the sample size they need or want. So one thing to think about is as your alpha goes down, you're going to end up with a larger sample size. So do you need a lower alpha? When would that be desirable? Of course, that's the idea of the false positive conclusion. If we really want to reduce that possibility, we don't want there to be any chance or a very, very small chance of concluding that the treatments are different when they actually are not different, then we might want to try an alpha, say, of 0.01. When is it okay, though, to go up? With alpha, maybe up to 0.10 instead of 0.05. Well, if the cost of a false positive conclusion doesn't matter, if it's pretty minimal, then that might be an appropriate choice. Similarly, as your power goes up, you're going to need a larger sample size, and that's a pretty intuitive conclusion. When do you need more power? Well, if you want to increase the probability of detecting that difference, if one exists, then you want your power a little higher, maybe than 80%. But if you're not worried about missing an effective new treatment, if the existing treatment is fine, and you're like, well, if we find that it's different, and it's a lot different, that's great, and if we don't find it, that's fine, then you can bring your power down a little bit. Another question we get a lot with sample size calculations is, where do I get P1 and P2? And of course, the relationship between them being the desired effect size. Most of that comes from either prior studies in the literature, formative work that you may have done with the population, existing data sets from similar treatments or comparable treatments, or consulting with experts about what's a good estimate for P1 and P2. Sometimes the desired effect size comes from, what would a funder or a Ministry of Health or an insurance company be willing to pay for? Are they going to need to see a 40 percentage point or a 50 percentage point jump in effectiveness in order to consider this new treatment, cost effective or worth implementing? So sometimes there are external forces determining what's an acceptable effect size. And of course, if you think about this and you look at the table and you see how sensitive sample sizes are to changes in things like effect size and P1 and P2, you can see how costly it can be to get this wrong. So it can be costly in that you determine a sample size much larger than you really need and you've spent too much money. Or if you've blown it and you've calculated a smaller sample size than you really need, then your trial's probably underpowered and you've basically wasted the money because you can't draw the conclusions, you can't really test the hypotheses that you set out testing. So those are costly in two different ways. Okay, one last word about sort of the ethics. There's been a big debate recently about whether we should think about underpowered studies being actually unethical. And why might we think of them as being unethical? Well, the idea is if you are going into a study underpowered, meaning you may not be able to detect any real differences between your treatment and control, you're actually putting subjects at risk, and you're probably spending someone's money to get probably not very good scientific information. There's a debate, and Schultz and Grimes enter that debate about whether we really think about that as unethical or just wasteful. One way to get around that, and we're going to talk about meta-analyses later on in the semester, but it may be that if you do lots of smaller studies that may be underpowered, you can eventually compile those results into a meta-analysis that does give you good information. So just keep that sort of ethical debate in mind when you're designing studies and when you're assessing studies for their power, whether it's appropriate, whether we're getting really good, useful scientific knowledge from that study. That's the end of Module 2. See you in Module 3. Except that I've got one more point. Another point that Schultz and Grimes make is that, yes, this power debate is very, very important, and we need to know, we need to do careful power calculations, but there are probably a lot of other aspects of the study, mostly around bias and internal validity, that may be even more important in conducting ethical, rigorous studies. So yes, power is important, but it's one piece of a larger set of design decisions that determine whether your study is really good or not.